Hi everyone, welcome back to a new video of the series where I share with you guys my equation sheet for the physics portion of the MCAT. Today I'll share the equations I think are the most important in the light and optics chapter of the Kaplan study guide. And I just want to clarify that these are not all the equations, but they are the equations that I thought that were the most important and the most tested in the full lengths I've done. This equation sheet allowed me to average a 130 in my Chem and Phys portion of my full length so far. So you can rely on it. And without further ado, let's just dive into it. So first off, we have the speed of light, which is known to be 3 times 10 to the 8 meters per second. So this basically tells you that if we know that the speed of light, which is c, is 3 times 10 to the 8, then the variables, or what's going to change, is the frequency and the wavelength. We know that the frequency is in hertz, or 1 over seconds, while the wavelength is in meters. And in this case, we can observe that when the frequency is going to go up, the wavelength is going to go down, and then when the wavelength goes up, the frequency is going to go down. So they are basically inversely proportional to each other. Here we have the visible spectrum. This is not an equation, but this is something that is heavily tested, and it's good to remember the order and the approximate wavelength for each of the visible spectrum, or the visible lights in the visible spectrum. So what I like to use is Roy GBV, which basically stands for red, orange, yellow, green, blue, violet. This is in the opposite direction of the spectrum, so R should be on the right and then V is on the left. And one trick I use is I know that in front of the visible spectrum on the red side is the infrared, and then on the end is or past the violet is the UV, and the wavelength increases going towards the right. So red is the first, orange is the second, yellow, green, blue, and violet, and then red is approximately 700 nanometers wavelength, and then violet is 400 nanometers wavelength. All right, the second would be the law of reflection, which basically states that when light is reflected on a reflective or a mirror or something like that, the incident ray and then the ray that gets out, if you draw a middle line here, then the angle at which the ray comes in is going to be the same angle as the ray comes out. So alpha 1 here is equal to alpha 2. One of the most important equation is here for spherical mirrors, which can also be used for lens as well, would be 1 over the focal length. Focal length is the length from the mirror to the focal point, which is here, is equal to 1 over O, which is the distance between the object and the mirror, plus 1 over E, or I, which is the distance the distance of the image from the mirror, and R, which is the radius of curvature, which is basically the distance between the C and the mirror, and C is basically 2 times F. So if C is 2 times F, then we know that R is 2 times the focal length. So the focal length is basically R divided by 2. Another important thing is the magnification of the image, and then this definitely makes sense, right? Because basically the magnitude, or how big is an image, is basically its size divided by the object size. So obviously if it's bigger, then the image size is going to be bigger, so magnitude is going to be bigger than the object. So M is basically the ratio of the image size to object size. And then if the image is upright, then the signs here will cancel out and you'll have a positive coming out. And then if the image is inverted, then this basically means that the image is going to stay is going to be positive, and the overall is going to be negative. So one thing I liked for the sine rule for the mirrors, which is pretty hard or can be complicated, what I like to think about is for a converging mirror, if you draw a full circle here, you know that focal length and the radius of curvature, the radius is inside the circle, right? You know, a circle, there's its diameter, and then half of its diameter is the radius. So you have the middle dot, and then if you link it to a spot of a circle, this is going to give you the radius. So what I like to think about is if the radius and the focal length are located inside the mirror, which in this case it would be for a concave mirror, then the F and an R are positive. If on the other hand you have a convex mirror, so if the light would come that way, then we know that the F is going to be here, and then the R is going to be here, and then they are outside of the circle. So in this case, the F and the R will be negative. So when you plot these into these equations, then they're going to be negative or positive depending on them being convex or concave. And then a real image, I is going to be above 0, and then a virtual image, I is going to be under 0. So basically a virtual image, or an image on the other side of the mirror, is going to be negative, and a negative image can be negative here, which is going to give us a positive, so the image is going to be basically upright. So what we know is mirrors, if we have an image on the back side, it's going to be upright. If we have an image on this side of the mirror, then it's going to be inverted. And then O, we can assume that it's always going to be positive for a mirror. Next would be refraction. So the index of refraction is equal to the speed of the light divided by the speed in the medium. So there's not much to say about this, it's just C over V, so N equals C over V. And then the Snell's law basically states that the index of refraction for a ray, index of a refraction for ray times its angle is equals to the index of refraction in a second medium times the angle number 2 to that to the normal. So this basically means that if the index of refraction for this is higher than for this one, then for it to compensate, this angle is going to be higher, right? So if you go from a smaller index, for example, if you go for a smaller index, from a smaller index to a higher index, then the angle to the normal is going to go down. And then something that it's not super important, but it's important enough to mention, If the N1 is higher than N2, then we know that the angle is going to be the angle at which there's the angle for N2, so alpha 2, is going to go down, or it's going to go up. It's going to go up, so it's going to go away from the normal, and then going away from the normal at some point, it's going to be basically 90 degrees, which means that if the alpha 2 or the angle 2 gets above 90 degrees, then it's going to basically refract, and come back in the same medium as it came from. And then this angle, it's a lot easier. It's a lot easier to explain when you can actually draw it, but I suggest you go and read about it or try to watch a video if it did not make sense. But the critical angle can be calculated using the invert function of sine with n2 over n1. Now let's go with the lenses. So lens are the opposite of mirrors, where for a convex lens they're going to converge, and then for concave lens they're going to diverge. And then here it's also the opposite for from mirrors. The positive F and R's are on the other side of the ray coming in. So if the ray converge toward this focal length, which is the positive side, then F and R are going to be positive. So for converging ray, concave lens, F and R are positive. For concave lens, where this diverge, and then we use, this dotted line, we use this F here, which is on the negative side, then F and R are negative. So here's sine a rule for lens. These ones stay the same. F and R, they're basically switched. So positive for convex lens converge. Negative for concave lens diverge. Important to mention that power of lens is equal to 1 over its focal length. So 1 over meter, which is also which can also be used with a unit of D here. And then here I have a little note where it says diverging lens. So diverging equal negative F. So it's going to be negative P, right? Just talked about this. Converging lens is going to be a positive F, so positive power. Here it basically says that multiple lens system, if they're in contact with each other, so if you put lenses together and they touch each other, then you can do 1F equals 1 over F1 plus 1 over F2 plus 1 over F3, blah, blah, blah. We know that 1F is power, so it's basically this also mean that power equal power over 1 plus power over 2 plus power over 3. The numbers 1 and 2 and 3 stands for the lenses that are in contact for each other. If they're not in contact, then we can use the magnification of each lens, and then you multiply them, or you can find the final magnification by multiplying each of their magnification together. I did not use this these equations yet, so I wouldn't be bothered about it. This is one of the hardest subject, I thought, in the lighted optics, which is diffraction, which basically means that it's the light when it enters a small opening, and then it diverges, and then gives black spots and all that stuff. So in the MCAT, they test two possible diffraction: single slit with one opening here, or double slit with two opening. So here, for a single slit, you have this formula, which is the slit width. So the width of this slit here, times sin of the angle, the alpha, which is the angle from the slit to a dark spot. So here we have light, dark, light, dark, light. So we kind of have a wave here. So we have the dark spot, which would be N1, second dark spot, which would be N2. So this length, or this angle, alpha here, can be plotted or put in as this alpha. So slit width times sin of alpha equal n, which is fringe numbers, so fringe, one of these fringe, N1 and 2, times the wavelength of the light. And for a double slit, it's similar. It's a single slit, but instead of the slit width, it's going to be the distance between the two slits. So the distance here times sin of the angle, again. But the angle starts from the midpoint of the two slits to one of the fringes, is equal to n, so that the fringe you use, n2 plus 1 over 2 times the wavelength of the light. So I suggest to spend a little time on this, but I have not been tested a lot on this, so I don't think it's super important. But if you want to get a good grasp of it, maybe watch a few videos or read about it, and then come back to this explanation or these equations, and it might make a little more sense. So I hope this helped, and this was all I had for the chapter about light and optics of chapter 8 of the Kaplan book. Thank you.